Well, let me welcome you to the Westmont Downtown Lecture Series. We always try to have as many introductions as possible to make the speakers nervous as possible. I'm Ken Kilstrom. I'm a member of the Westmont Foundation Board and an emeritus physics faculty. And I get to introduce the person who's introducing the speaker. So that tells you how important I am. Anyway, so the Westmont Foundation Board sponsors a series which it's begun over 2 decades ago. It highlights topics of the day, has the most amazing Westmont faculty to bring information to you, and if they're not available, I've done 1 or 2 of these. The series is meant to be a gift to the community. The goal is for those who attend to have meaningful conversation, to be able to ask lots of questions, all the questions you want. The more you can put Ben on the spot, the happier I'll be. So don't be shy. You can also mark your calendars for the next Westmont Downtown, which is going to be Monday, so not Thursday, Monday, December 8th, also at 5:30, at the same place right here, Community Arts Workshop, where Westmont history professor Alistair Sue is going to be speaking on tariff nations, the rise, fall, and return of America's most contentious tax, tariffs. Anyways, I'm pleased to introduce Dr. Leanne Dubinsky, and she'll in turn introduce Ben. Dr. Dubinsky got her PhD from the University of Georgia, the land of the Bulldogs, and is Dean of Faculty Development and Global Education at Westmont. And Westmont is known for their off-campus programs. She was previously a professor of leadership at Asbury Theological Seminary in Kentucky. So if you want tips on the Derby, family recipe for bourbon, she's your gal. And associate professor of intercultural education at Biola University, a longtime athletic rival of Westmont. So I promised her I wouldn't lead us in the beat Biola chant. Before teaching, she served 18 years in cross-cultural ministry. She's the author of Confronting Sacred Inequalities, Creating Christian Organizations Where Women Thrive, also Playing by the Rules, and co-author of Glass Walls and Women in the Mission of the Church, as well as numerous journal articles. So thank you, Leanne, and come up and introduce yourself.
Good evening. I kind of think I want to hear the chant. Maybe afterwards. So it's my great pleasure to introduce Dr. Ben Carlson. He earned his PhD in physics from Carnegie Mellon in 2015 and then worked as a postdoctoral researcher at the University of Pittsburgh until 2021 when he joined the Westmont faculty. His area of research is experimental high-energy physics, and he works on the ATLAS experiment in Geneva, Switzerland. In particular, he looks for hints of new particles in decays in the Higgs boson. Ben also works on the ATLAS trigger system, which determines in a fraction of a second which collisions should be saved. He was awarded a National Science Foundation grant in 2022, and at Westmont, he teaches a variety of challenging physics courses covering fundamental topics like special relativity and quantum mechanics. Foundations of issues related to climate change are often examples in these courses, and furthermore, in general ed, physical science courses like Physics for Future Presidents, issues of physics concepts are used to frame the topic of climate change and energy. So tonight, he's going to be talking to us about energy and climate change through the lens of basic science. Let's welcome Dr. Carlson.
Thank you for the introduction and for coming tonight. So yeah, I'm going to tell you about this topic that is, I think, very exciting and interesting and challenging and relevant to everyone. When I was first asked to give this talk, I was like, oh, is this a typo though? Because my field is high energy physics. And they're like, no, we want to talk about energy and climate. And I think it kind of makes sense. In my classes, this is a theme that whenever I can, I really try to emphasize. And when I did teach this class, this physical science class, when I teach it in the future, I think one of the main draws for how I teach it is the fact that it is integrated into something that people really care about. So that's kind of the theme that I'll be taking tonight. Now, you should know that I'm a high energy physicist, not a climate scientist, and I'm not a policy expert. So those are things that are a little bit, there are ways to get much more specific. So I think my approach might be unique to some extent in the sense that we'll be emphasizing more things like, what is energy, what is thermodynamics, and how does quantum mechanics, and how does it all play a role in these basic issues. So that's my approach. I'll just give you a little bit more background. So, what is the Large Hadron Collider and the ATLAS experiment? This is where I spend my research time. So this is an experiment in Geneva, Switzerland. It's about 27 kilometers in circumference. So if you were to ride your bike around it, it would take you most of the day. And then what we do is we take beams of protons, which are essentially strip off the electron of a hydrogen atom, and then accelerate it using electromagnetic cavities to close to the speed of light. Look at all the digits there before c, which is the speed of light. So they're very high energy particles. Smash them together, observe what happens in an experiment like this one, the ATLAS experiment, which is one of the most complicated cameras in the world. And then we look at what happens in those collisions to see what are the fundamental properties. Now, most of these don't have to do with things like building a solar cell, but 50 years ago, this type of work, in some sense, did. Because Westmont is an undergraduate institution, I'm also working with undergraduate students. So one of them is here tonight. He helped me with the demo. The 4 on the top have graduated and got onto graduate programs and industry positions. And my group, what we focus on is the Higgs boson, dark matter. We don't know where it is. We're trying to make it, find it. And then AI, machine learning tools for what's called the trigger. And I can talk to you more about that after if you're interested. But those types of things have to do with kind of specialized computing hardware that is more complicated than what you can just buy off the shelf. We also are involved in work at the actual physical experiment, obviously not while we're doing classes, but over the summer. Many students have traveled and worked on things like ensuring we collect high quality data. This is a sort of picture of one of the collisions. And so we look at, say, several million of those in the form of histograms to make sure that what is coming out of the experiment actually makes sense. We also work on things like installing physical hardware. We're going to come back to this when we talk about AI, but doing computational work that involves computers. So my students have been involved in installing those. And then my research kind of intellectual contributions involve things like designing physics algorithms to go into these custom chips called FPGAs. You can't quite see it here, but there's like a map of where those physical logic gates get implemented in the chip. So that's what my research job is. Today I'm going to tell you about something different that is related and builds on those topics of physical science. I'm just going to try to move this up here. So the outline of my presentation is that I'm going to tell you a little bit about kind of global warming, just the kind of facts, the history and the basic science. Then I'll tell you about how that transitions to solutions in the future involving energy and well in the next 20 years. So let's start with a quantitative observation. If you were to take the temperature across the globe, not just in one location, but across the globe, make sure that those measurements are very good in terms of minimizing kind of unwanted effects. And then look at that change in temperature with respect to a baseline. This baseline is from 1951 to 1980, which is a common but not the only baseline. And then look at the so-called anomaly, or the difference from that average value. What you see is that those temperatures go up. And the value here is just about 1 degree centigrade. There's very little controversy about this. To a large extent, this is well accepted in the sense that it is more or less just a measurement or an empirical summary of all the different types of temperature measurements that are happening on the Earth. Now, it is a little bit tempting and somewhat justified to ask the question, it seemed a little hot this year. Is that something that is real or not? And so I made this myself using data that you can just get online. And what you can see is the red is the global average normalized in the same way with respect at about 1950 to be 0. And you can see, again, this temperature increase of about 1 degree. The blue is Santa Barbara, so you see it's like jagged, it's up and down. Sometimes it's a little colder, sometimes it's a little bit hotter. So averaged over a year. So could you tell? Maybe. Might be a little bit of a hard signal to feel without having this sort of quantitative data. So let's do a little bit of history. So we know the world is warming. When do people start to first think about what could cause these effects? So one of the first people to observe a warming effect in gas, carbon dioxide gas, which is part of the atmosphere, was Eunice Foote in 1856. This wasn't known that she did this until about 10 years ago, or at least it was not widely known. But the basic experiment is really simple and ingenious. The idea is you take a bell jar, and you put one in the shade, you put one in the sun, and you see which one gets hotter if there's some gas inside of this jar. Then she put different gases. Sorry, I'm just trying to move slightly away from this light. Can you still hear me?
Yeah.
Okay. So put slightly different gases into this jar, including carbon dioxide. And the conclusion is that if you increase the amount of carbon dioxide, then it would slightly increase the temperature if you were to, say, scale this up to the planet. Now, I don't think at this point they had in mind the scale of this issue, but she was the first empirical result that shows carbon dioxide causes a warming effect. Keep in mind, in 1856, they don't know that there are atoms, they don't know what carbon, they know the name of the molecule, right? They call it, it's not called carbon dioxide, it's called something else, but they know the substance, but they don't know very much about it. So this is very much an empirical result. And by the way, the question that she was trying to answer was not about global warming, it's about why mountaintops are colder than valleys. So she doesn't really get credit for it, but now we know that she's the person that really did this. So about 50 years later, another, in this case, very well-known scientist, Arrhenius, the chemist, walking through Stockholm and just watching all of these coal stacks pump emissions into the atmosphere. And he thinks, well, I'm a chemist. I know that carbon dioxide has these properties. I can actually figure out quantitatively how much this would increase the temperature. And then he says, you know what? Let me calculate how much would happen if CO2 on the Earth doubled from these smokestacks. He knows enough about how combustion works, and he knows enough about CO2 that he can actually do this, and calculates within, given what he knows, he says, well, you know, I think there could be like an increase of a few degrees centigrade with a doubling of CO2. So pretty amazing calculation, 1896 to 1906. By the way, in those 10 years, he also wins the Nobel Prize in Chemistry. Not for that, but interesting fact right in the middle. Okay, so what do we know? We know the temperature of the Earth is increasing. We know that empirically, there's evidence that carbon dioxide could cause a warming effect, and Arrhenius calculated it. Let's kind of think from our perspective instead. So let's think about what could be causing this warming effect based on everything that we know, including these empirical effects about carbon dioxide. So maybe the warming effect is caused because the sun is changing in its luminosity. It's a good hypothesis. It's a good question. That might be what's causing this temperature change. Maybe it's that the Earth is slightly wobbling. Or maybe it's that the distance between the Earth and the sun is slightly changing. It gets a little bit closer, it gets a little bit warmer, right? Maybe volcanoes are contributing carbon dioxide, and it is a real greenhouse gas effect, but maybe volcanoes are contributing most of the CO2. So these are all things that could be contributing. I like to think of it this way because this is how science actually works, right? We have an observation, we have a series of ideas about what could explain it, and we try to go through all of them. And now comes the hard part because we have to do the actual calculations to see which of these effects could be causing it, and or other arguments that might exclude some of them. So let's go through them. This top one here, the solar cycle, that's too short. That's 11 years. That can't explain it. These two are way too long. They're tens of thousands of years. And we see variation on the scale of like 50 to 100 years. So that's not going to work. Volcanoes, good idea, but we can measure the amount of carbon dioxide that humans make and volcanoes make, and humans just make way more. 2 orders of magnitude more, 100 times more carbon dioxide, so negligible effect most of the time. Some subtleties that I'll come back to later that have actually to do with cooling and sometimes warming. So what are we left with? Well, I told you that we have this empirical evidence about carbon dioxide being warming. We don't know why, so let's use our modern knowledge of chemistry and physics. We know that it's actually a molecule made up of carbon and 2 oxygen atoms. That's what CO2 means, right? And we also know just in practice that in the process of combustion and burning fossil fuels, we emit copious amounts of CO2. So this is the hypothesis that we're going to investigate in more detail, while also making these more quantitative. So before we do that, I need to take a little bit of a detour to tell you about radiation. So end of the 19th century, if you take say a steel rod and insert it into a fire, it glows, right? And so people did measurements where they measured how brightly it glowed, and the so-called intensity is a function of wavelength. So if it gets a little bit darker red, it's a longer wavelength, and it's a brighter yellow and then blue, this would be a lower wavelength. And they said, well, look, we have a calculation that we can model this thermal effect, and it just increases. But we actually have all of these measurements with these data points here that turn over and fall back down. This was really important in physics because it showed that our understanding of thermal motion was just wrong. This has a name. It's called the ultraviolet catastrophe, because we just can't explain what happens over in this region of low wavelength, which is the ultraviolet. So Planck comes along and says, I know what's going on. You need to have something called photons, which are packets of energy that describe light. And so this is a quantum because it's coming in these packets, and therefore the sort of birth of quantum theory. And that predicts these dots. We also learned that there's this peak to these dots, and this has a semi-empirical law that says that the peak decreases as the temperature increases. So this peak has to do with the temperature of whatever the spectrum, which is called the black body spectrum, comes from. Not really related to climate science, but it's cool physics. The cosmic microwave background, which is sort of the thermal energy left over from the Big Bang, they have a temperature of about 3 Kelvin, which is very cold, and they follow a perfect black body, the best black body that anyone has ever seen. Also a Nobel Prize in 2006. So lots of really basic science there that is super relevant, because if you think about the Earth-Sun system, then these two distributions are critical. First, you have the sun, which is about 5,000 Kelvin, with a distribution that's peaked in the visible. So when you walk outside, you see the sun. Most of the energy is in the visible regime. So short wavelength radiation because it's very hot. The Earth is not 5,000 Kelvin. The Earth is about 300 Kelvin, or room temperature is about 70 degrees or so Fahrenheit. And so the Earth is also radiating because it has some temperature associated with it. But because it's so cold, this peak is shifted out to much longer wavelengths, which are in the infrared. So, sun absorbs energy over here, Earth emits it over here. Well, what else do we know about the Earth? Well, it has all these gases in it. The one that is really important, although the main important one, is carbon dioxide. And in chemistry, you learn that these form bonds, right? So bonds are the way the electrons are shared in a way that attaches the oxygen to the carbon. And what happens to carbon dioxide is that it can vibrate back and forth in different ways. This is one way. It's called the asymmetric stretch. And I'm going to show you a physical model of this. Can you turn it on? This is an image, but this happens in real life with masses and springs. If you want to know how to understand the world, you masses and springs.
You want to do it or me?
Go ahead.
Okay. So I'm going to displace these outer ones inside a little bit. And then here in the middle, I'm going to displace this cart to one side. So I displace the outer ones the same distance closer in. And now I've displaced the middle one in an asymmetrical manner. Now I'm going to let it all go. You can see the outer ones kind of follow the same like period. They both move equally and opposite to each other. But this middle one will move asymmetrically to the side. Those go the same up and back, and this one moves asymmetrically in the middle next to them.
So you can come look at the experiment afterwards if you want. But all that we have here is carts on this almost frictionless track. There's a little fan that's blowing air so that it doesn't get stuck on the track. And then the two springs are like the bonds. So what you see in this little animation, that's real. That's something that happens with masses and springs. The bond is like the spring. The atom is like the mass. The thing that you can't tell from the masses and springs is that this particular mode is one that happens to absorb infrared radiation. So remember, the Earth, emitting infrared radiation, has some carbon dioxide in the atmosphere. Carbon dioxide can be excited in this particular way, which absorbs infrared radiation. By the way, this whole chemistry here, this is all quantum mechanics. It involves the quanta, in this case, the amount that they can vibrate back and forth. That's something that is described by physics. We can calculate it. We can measure it in specific experiments. Any chemistry lab can measure this. So let's now zoom out to a big picture effect. Sun, radiation coming in. There's a lot of numbers here. In my class, we calculate all this stuff, but I'm not worried about it here. Energy coming in from the sun, hits the Earth, is re-radiated. Now, some of the light or the energy gets reflected back into space by, say, clouds in the atmosphere. Some of it by the surface, depending on if it's water, snow, forest. Varies a little bit, but on average, some of it gets reflected back. And then some of it is this infrared radiation from the surface, which then goes through all these many different things here. The relevant one being the greenhouse gas, which is the carbon dioxide. And this could absorb just a little bit of that energy. What can happen is that the carbon dioxide, it starts to excite instead of re-radiating some infrared radiation, it just kind of warms it up just a little bit. And so this can trap just a little bit of energy in this layer in our atmosphere. So if you think about our hypotheses, this one seems to be the one that's holding the best, because we really understand exactly why. We can do all these experiments in the lab. We can tell you precisely, how much or why, from a very basic sense, it would trap infrared radiation. So let's do a little analysis of the data that I showed you, but this time, instead of showing the global temperature as a function of time, I'm going to plot on the x-axis the amount of carbon dioxide in the atmosphere. The units, those are called parts per million. They just have to do with a measure of how much carbon dioxide. But really what you want to look for is how this number is increasing as we go forward. We started in 1850 at about 280. We're in 1990s, we're at 350. 2010, we're about 380. So now we're in the 400s. So 1, concentration is increasing. 2, the global mean temperature is increasing as a function of carbon dioxide. And so to me, this is one of the most amazing ways to understand the attribution of the global mean temperature, because it shows that these two things are correlated, as you would expect. You've ruled out all the other hypotheses, and it really shows you clearly that carbon dioxide is the thing causing this. Over here, it looks like a line. It's not a line. It's a log. That has to do with the fact that as you add a little bit of carbon dioxide, it traps some of the radiation. Oops. And you can fit this, and you can extrapolate forward. In fact, this is so simple to do that I did it as a student project. So you go into, there are two databases, which is kind of annoying, but You get some temperature on the y-axis, you get the concentration on the x-axis, correlate them together, and then do a fit and reproduce that plot. And also, you can do an extrapolation into the future. So this is where we are now. If you doubled the carbon dioxide again, temperature would increase by about 2 degrees with respect to where we are now. This is not a model, right? I didn't do any complicated simulations of the atmosphere. All I did was just take the data and some basic science about how carbon dioxide traps heat, and I can get a pretty clear picture of what might happen in the future. If you're a climate scientist, you put a lot more detail into this type of work. But as a student project, I thought this was cool. I couldn't find something like it, so I made it. Okay, so we went through all these hypotheses. Let's make it quantitative. This is a summary plot that shows many different studies put together, and I find it extremely helpful. So let's start with our hypothesis of carbon dioxide. We can start with any of these, but let's start with that one. Over the last 10 years, the temperature has changed by about 0.2 degrees, and we can do calculations to see how much carbon dioxide we emitted and how much temperature change we could attribute to that. And it's substantial. Now, everything else here, some of them are significant, but they're fluctuating. So this El Nino La Nina cycle, there's natural weather patterns. It gets hotter and colder. Those are short-term fluctuations. Solar cycle, I told you that was 11 years. Look at this. 10-year cycle, you see it going up and down. This was a volcanic eruption. You see there's conflicting estimates. There's a lot of things going on in eruptions, and this one in particular. There's water vapor, there's sulfur dioxide, so there's competing effects here. It's still not enough to explain what we see. This one here, look closely at this. Nothing, nothing, nothing. 5 years ago, all of a sudden, this contribution from what's called marine fuel pollution starts to turn on, which means we have a big effect of temperature rising. So what is that? This is a map that shows you the sulfur dioxide contributions from shipping in these different regions of the world, and you can see that it's very high where there's a lot of ships. What sulfur dioxide does is the opposite of carbon dioxide. It reflects sunlight, which means that there's a net cooling effect. What happened 5 years ago? There was legislation and international agreements that required ships to be cleaner and have less pollutants. And as a result, there was a little bit of warming that occurred in the last 5 years because there's less pollution going in the atmosphere that otherwise was reflecting sunlight. Bad for other reasons, but was slightly cooling, especially locally in these places where the concentration was higher. So what do I want to take? I want you to take away from this is climate scientists in particular have a detailed picture of all these different pieces, calculate all the different effects, really carefully consider what could be causing global warming, and the best explanation is that it's carbon dioxide and that it's caused by humans emitting it. Now, this might not be super helpful for you, but for me, this is a very helpful way to think of it. This is the discovery of the Higgs boson. This is the mass. It's just a variable that you can calculate in your data. And what you see in these black dots are essentially the number of collisions that you observe with that property. The red is a model that predicts the background. So it's a hypothesis of what can happen in the collision. And the blue is a different effect. So you have these the purple is a different effect. So you have these different effects. You calculate what they are. They're very complicated models. We do them with Monte Carlo simulations. We have massively complicated computing resources to do this. And then we have one more hypothesis, which is, what if I have a new particle, which is the Higgs boson? Where would I see that? And you would see it right here. So when you interpret that data, one, you cannot explain it with the existing models. You cannot explain it with your hypothesis that it is whatever this red thing is. That can't explain what's happening in this data. Also, you have another picture, which is that if I did have a new particle, it would populate this type of shape right here. And that means I've found something new. In this case, it was a Higgs boson. About a little over 10 years ago, got a Nobel Prize for it. And, well, some people did. In theory, not in an experiment, but in theory, got a Nobel Prize for it. So I want to say that the mechanisms of thinking are exactly the same. There's nothing, sort of odd about how climate science is working. It's the same as how every other field of science works. And if you read the sort of very large reports like from the IPCC, it shows the same type of calculations, human influence, other factors, and these are different ways of showing essentially the same thing. Slightly different years and parameters and so on, but the same effect. And the conclusion is humans are the dominant cause. Scientists largely agree. Now, I personally don't find that to be the most interesting thing to talk about. I'm much more interested in talking about the science, but imagine that you have a lot of people with PhDs trying to disprove each other. What you're going to do is think about all these hypotheses and calculate them, and people can't think of other solutions that work. So that's what this really says. My professional organization also agrees. I think that has some weight. But I'm much more interested in talking about the why than who said it. So now I want to shift a little bit, and I want to talk about where do the emissions on the Earth come from, what are the impacts, and then what can we do about it. So if you look at the Earth, the emissions that we have, yes, carbon dioxide is most of our greenhouse gas emissions. There's other things I didn't talk about, similar effects. Methane, for example, is something which is a potent greenhouse gas, so you don't have to emit very much of it. But if you do emit some, it can make a big effect on warming. And the reason, and one of the places you get it is in natural gas wells, have methane in them. Obviously you want to burn it, it's very useful, but you can also have leaks. And so if you just look at this natural gas well, no leak. If you look at this one with a special camera, you can see that there's methane pouring out of this. So that's like one of the sources of methane and one of the big concerns. So what are the consequences? So let's think about one that you've heard about that is probably the most obvious, which is sea ice and sea levels. In this little video, you can actually see in each year what the coverage is in the North Pole every year. And you can see, it's fluctuating up and down a little bit, but let's let it keep going. Over time, the polar coverage of sea ice is decreasing. Every year it's going down a little bit. So that's one effect. It can have serious knock-on effects. Now, there's also the effect of sea level rise, which, you really can't see that. I'll just try to point it out here. So this axis is the amount that it rises. The maximum is just about 20 centimeters, so it's only about this much. This doesn't come from sea ice, right? But it does come from effects that involve things that are like glaciers, the Greenland ice sheets, the Antarctic ice sheets melting. And this is time. So as we go forward, you see this increasing and increasing. In this intermediate region in the 70s here, this is this really interesting effect where basically water gets trapped in dams. And so because of this water impoundment effect, it doesn't go up as rapidly here. So that's calculated and known. Now, the rising popular thing is hey, it's happening because the ice on the land is melting. Yes. Also, it's thermal expansion. So if you imagine a bridge has these buckles at the edge, as it heats up, the bridge expands, so you need to be able to allow for that expansion. Same thing happens with water. Even though the warming is not happening uniformly, there's enough here that thermal expansion is a piece of the warming effect. And so it's only about a quarter or so of the warming effect, but it is a piece of it. Most of it is due to added melting ice. And so where we are now is that we're somewhere tens of centimeters of sea level rise, which is not too significant, but it's one of the more obvious effects. You can measure this with satellites, the sea level went up by a few centimeters. Longer term, there are predicted to be many other consequences, which you read in the news all the time, right? And this is where I think it gets not necessarily controversial, but more complicated. But there are some things that are that IPCC report, for example, says that they have pretty good, they have pretty good knowledge of things like wildfires, and heat waves will be getting worse as the temperature of the average temperature of the Earth increases. So there are all these consequences, and just pull up the news any given day, and you'll see all kinds of issues that might happen, and also potentially things we don't know about yet, which might happen as a consequence of the global temperature increase. So what do we do about it? Here's some driving questions that animate the rest of this presentation. One, how does the electrical grid or energy just in general fit into the big picture? Energy that we use in the forms of transportation and the electrical grid, see they're kind of related. What are the non-fossil fuel alternatives and where do we stand now? And then what are the opportunities and challenges? And this is going to be very high level, partly because if you think about what goes into this question, alternative energy or just energy in general, there's just so many different elements. Like there's the fundamental science on the one hand. You need to have electrochemistry to make batteries. You need to have solid state physics to make photovoltaic cells. You need to have nuclear physics and nuclear engineering to make power plants. You need to do fundamental science to discover things you don't know that you needed. All kinds of stuff here that is going to go into this. Then there's the engineering question. Can you scale up solar, wind, nuclear fission? Can you scale it? Questions of economics. And then where our energy is adopted kind of sits in the middle of all of this. And this doesn't happen in a vacuum. It happens because companies and people want it and because we have legislation and funding that provides incentives to shift. And so to shift how we get our energy. And so this also involves this big kind of messy platform of policy and government somehow involved in this. So there's just a whole lot that I'm not going to get into, but I just want to give you a sense of like all the different elements that we would need to address. Now, I'm mostly going to talk about sort of the energy grid, but you can think about the sources of emission as a framework for that. So in the United States, roughly 25% of our emissions come from electric power, 27% from transportation. Industry would be like steel and things like that, and then heating in our homes and agriculture. So this would be more of like, this is sort of a different topic, but essentially like what the things we do in our farms, they also have emissions. So that's what's in this part of the pie chart. Globally, it's much more complicated for a lot of reasons, but you do still see that electricity and heat is a big piece of it. So if we were to focus on something, this would make a lot of sense. Electricity, heat, transportation. So what's the strategy? In general, what people say is electrify everything. If you want to take away something from this, electrify everything. That's the solution. Why? Well, take your cars, turn them into something that's powered by electricity. Take your heating, get rid of the natural gas, put in a heat pump, make it work by electricity. Then you shift all of these pieces into electric power, and one, that just is cleaner in general, and two, you can make the electricity renewable or have no carbon emissions, and you can do it in one place, in one plant, and then have minimal kind of carbon emissions for all these other things. So that's what we want to do in order to mitigate this problem. That's the strategy. It would be helpful to see kind of where we stand now. I realize this might be a little small to read, but I'll just kind of highlight the key points. This is as a function of time, and this big brown part here, that's coal. So that peaked at a little less than half of the electricity in the United States in about 2005, and it's been falling ever since then. Globally, it's fallen to record lows in the last year, so coal has been falling. Natural gas has been filling out part of this pie chart and even expanding, while renewables, including nuclear energy, wind, hydro, all these things have been filling out the rest. So if you just had to have a quick takeaway number, at the moment about 60% of our total energy comes from fossil fuels, glass half full. About half of that is coming from renewable energies or things that don't have a carbon footprint. Looking forward, I want you to remember this through the rest of the presentation, we're going to need more energy. So how do we fix that? Turns out that our nuclear power, which is this red, that's falling off. Plants are getting old. So that's decreasing. Coal is decreasing. So we're going to fill the gap. nominally with renewables, keeping natural gas the same. Now, keep in mind, this is somebody's projection. It's not a plan. You can change this, right? You can build different kinds of power plants. But in this projection, if you sort of take reasonable assumptions about costs and so on, this projection is that we would not really see much change in the next 25 years in our fossil fuel consumption for electricity plants. Also, this plot is like 3 years old, and it does not include AI. So that's a factor that could push up this usage even farther and accelerate the usage of some of these fossil fuels. So we'll come back to that. Now, in the US, the left-hand side is a pie chart version of what I just said, mostly fossil fuels. We have about 60% of our energy in the electric grid coming from that. But in the rest of the world, that's not necessarily the case. So there are examples, for example, Switzerland, which I picked because I live there, but also because you'll see that most of their energy comes from things that have no carbon emissions. So hydroelectric dams, rivers, nuclear, solar, and just very little fossil fuel-based emissions. So why do I say this? It is possible to have a more sustainable mix. The US is a complicated place in the sense that we're very large. We have a lot of different needs, and you don't always have the hydropower resources that Switzerland does, but it is possible to do. So one question before we go into all these details about what could we do, what are the sources, how do all these things work, is it too late to prevent the effects of climate change? Part of the answer is yes. We have already warmed the world by about 1 degree. Some of that is baked in. We could flatten it out so that it doesn't warm as much. So that is still possible, very much possible. It's just that it would require action now. Second thing, if all this carbon dioxide was emitted and is in the atmosphere, do we need to think about taking it out of the atmosphere? Controversial. Because it might justify emitting more from other fossil fuel plants. So people are not uniformly in agreement that this is a good idea, although the IPCC does include this as something that needs to be seriously considered. So at this point, I'm going to tell you a little bit about just types of energy and some kind of basic physics concerns with these. So I'll talk about fossil fuels, because that's the baseline of where we are, and then what we would call renewables, how you store that energy, and then I'll spend quite a bit of time talking about nuclear energy. So first of all, if you've ever gotten a bill, units of energy on here are kilowatt hours, kWh. And that's what we get most of the time, that's what we get billed in. So I pay a certain amount for each kilowatt hour, and those are the units that you'll see in terms of what a power plant or what a user will consume. So how do we think about these different types of energy in terms of physics? Well, the way I like to think about it, which comes from Physics for Future Presidents by Richard Miller, is to think about the energy density per gram. So think about the mass, fill it up with a different type of fuel. How much energy is in there? It turns out that in terms of energy sources, fossil fuels like natural gas actually have a tremendous amount of energy density in them. That's why we use them, right? I mean, they're great sources of energy. So the thing that's easiest to understand here is this ratio to TNT, which is a little bit surprising. So the natural gas has about 20 times the energy per gram as TNT. And the reason you think of TNT as being so, you would probably not think that. The reason you think that TNT has so much energy is because it all releases it at one time. So there's this explosion effect, right? But in terms of energy density, natural gas is one of the highest substances that we can readily get. Chocolate chip cookies are not bad, but probably not super economical as a source of energy. But there's sugar in there, right? That's why it's so dense. And butter, things like that. And then auto batteries are on the chart in a significant way. And when this book was written that I took most of this table from, this number was lower by an order of magnitude. The very pessimistic chapter about electric vehicles in this book. Turns out that was wrong. So I updated this number about a year or two ago. So it's closer to what we are at now. But even it just shows in the last 10 years how much difference there has been, at least in this particular entry for energy density. When we burn fossil fuels, what happens? Well, we extract chemical energy, turn it into kinetic and then electric energy. You have a very complicated combustion system, but really this is limited by a pretty basic concept called the Carnot cycle. What happens is you have work being done because the volume of, say, a cylinder is changing, and there's this basic cycle here. If you're interested in thermodynamics, maybe you've seen this, but it converts the heat from the explosion into useful work and dumps the rest in the cold reservoir, say a river. And the efficiency is always less than 1. Notice there's a less than or equal to here. Efficiency of this process is always less than 1. And it has to do with the ratio of the two temperatures, which turns out for most systems is 20%. So these are not particularly efficient. What you care about in some sense is not the efficiency, it's the dollar, but it is an interesting measure and some really basic physics. Also applies to power plants. Turns out that natural gas, coal, nuclear, all these things use the same basic process. You heat up the water with steam, goes through a turbine. So nuclear is also limited by this effect. Most of the renewables are not. So things like wind and solar, these generate electricity actually much more efficiently by directly converting, say, light into electricity, or say kinetic energy from the wind into electricity. And you can see in this chart, the amount of these two that we're using, wind and solar, has just shot up in the last 10 years. And so it went from 300 billion kilowatt hours to 900 billion kilowatt hours. So a factor of 3 in just 10 years. Notice that hydroelectric is pretty flat. It is still a big chunk of our renewables, though. And interestingly enough, despite the fact that it's a big chunk, in terms of the energy density, it's tiny. If you have a 100-meter dam, tiny energy density per gram, but you have a lot of grams of water behind the Hoover Dam. And so this massive volume of water means we can actually get a decent amount of energy from hydroelectric. If you've ever been to the Hoover Dam, it's a really cool experience. But it's largely utilized. So what we have is going to stay for the most part. We're not going to add much more. There are some studies that show there could be some growth, but I think that it's also, from a water perspective, very expensive to install. What is cheap is solar cells, based on some solid-state physics. With silicon, essentially what happens is you have two layers which get doped with different charges, and so then there's what's called a band gap between them. So they have slightly different energies. It involves quantum mechanics, and then when the light comes in, it'll knock the electron across the gap, which then can be used in a circuit. You add up lots of these, wire them together in this sort of cell, then you can actually generate quite a bit of energy. And it converts about half of the energy from the light directly into electricity, which in a way doesn't sound like much, but it's higher than we were getting with fossil fuels. This number is sort of like the best we could do. Most cells that you would have in your house would not quite be there, but there are lots of technologies for solar cells, and they have been increasing. More important to the expansion of this technology is the cost. So over the last 10 years, the cost has really come down dramatically. There's a lot of stuff going on in these charts, which comes from the National Renewable Energy Lab. And you can see that these are coming down, but there's too many things going on here, so let's zoom in. You can see that if you just took residential solar, like if you tried to buy some to install in your house, this has come down by a bit more than a factor of 2. The cost for the panels is below $1 per watt. And then the other costs has to do with installation and stuff. But still well below $3 per watt if you were to say, walk away from the installation on your house, if it's simple. So huge reductions, and that's partly because we expanded, right? And now because they are cheaper, we can expand. So a little bit of a circular economic principle there. Similarly, wind. Turns out that you can generate lots of electricity from mechanical energy and wind. Each of these wind turbines generates 3 to 4 million watts of electricity. Each panel, each of these panels generates like 300 watts. So there's just a tremendous amount of energy from each of these. Can power hundreds of homes. And perhaps more importantly, broadly deployed across the US where there is wind that is common. I was going to West Texas a couple of years ago, and I was like looking out the window at night, and I was like, what are those flashing lights? Oh, they're windmills. The other cool thing about this is that there's potential for something like a factor of 100 expansion. Now, that doesn't involve all the politics, like who wants to have windmills nearby and all this, but the potential in terms of the resource is there. And the cost is competitive with fossil fuels. So this comes from the IPCC, and it shows that the cost is falling. It's not as fast as solar is falling, but it's in the range that is actually cheaper. So pretty amazing. This is for onshore wind. Offshore wind's a little different, but actually sort of similar story. All these renewables, especially solar, they involve storage. So for this, we need batteries. And battery technology has come super far in the last few decades. When I was a kid, if you had a battery-powered, like a rechargeable battery or something, you'd run your tape player for an hour and then it would be dead. Like they were just like totally ineffective. But now that's not true. And the reason is that the chemistry has improved such that the energy density, again, this concept of energy density, has been increasing. There's two measures, energy density per mass and volume. To build a car, they kind of both matter. You don't want it to be too big, you don't want it to be too heavy. But these are kind of related to each other, so just different axes to show the same thing. Also, perhaps more importantly, the cost is falling. So 2010, $1,000 per kilowatt hour. That's a unit of energy. So that would run your fridge for an hour. $1,000 for that battery. Now, $125. That's a target. That's about where we are. So almost a factor of 10 in reduction in cost for batteries. That's why there are electric vehicles everywhere, or it's this price because there are electric vehicles everywhere. Again, economic circle, not totally clear. But this is a good thing. It has made batteries very cheap. On the other hand, there are concerns, serious concerns, about what goes into a battery, right? We don't have all the supply lines in the US. So what is happening to get these rare earth materials for, say, building batteries? And so some of these are hand-dug mines, and so there's big concerns about that. There's also efforts to try to fix it, but at the moment, I think this is still one of the concerns. Also, environmental issue. Should we try to get this out of the deep sea? I like podcasts. This is a great episode. Should we try that? There's all kinds of environmental issues, but it would provide a source of rare earth materials for batteries. But I do have some concern about battery production. So one last thing in terms of storage, hydrogen, denser in energy per mass than batteries. This is a way of storing energy where you basically take water and split it into hydrogen and oxygen. And it's interesting. You can take a solar cell farm, you can split them. It's becoming much more efficient, so this is a form of energy storage which is serious. One issue, which might impact things like, say, having a hydrogen-powered car, is that in liquid form, the energy density by volume is very low. So it just takes a lot of space to store it. Potentially less of an issue if you want to, say, have a ship. So there's people talking about hydrogen ships and other alternative fuels for ships, like ammonia. We have to move the energy around the country, the electrical grid. There's some opportunities for improving that to make space for renewables, and also just reducing losses, but I'll skip over that for now. So I want to just spend a few moments talking about fission, nuclear energy. So by far, the highest energy density material that we have is things like uranium. Very energy dense, 30 million times as dense as TNT. So what are the mechanisms and issues there? So for uranium, which happens to be the material that was used in the first atomic bomb as well, the process is that one neutron will split this into two daughter isotopes and 3 neutrons. Because there's 2 additional new neutrons, this can cause a chain reaction to have this process occur over and over again. And each time this splits, there's an enormous amount of stored energy that was in that nucleus that is released. That is where the Earth derives most of its heat in the form of geothermal. So that's one way we could get energy. There's some room for expanding that. We could also make reactors, and this is where we get most of our energy from nuclear fission at the moment. The idea is that you actually don't need very pure uranium, and you can control it with these rods. They slow down the reaction and mean that it can't explode like a bomb. A bomb, what you do is you have to have every piece of uranium undergo fission within a very short amount of time, so it releases all of its energy at once. That can't happen in a reactor. So from that sense, it's quite safe. There's other issues about controlling it, as you all know, but it certainly can't explode from the fission reaction. It's also, you could replace all the coal in the world with like 1,000 tons of uranium. So pretty nice translation in terms of energy density. We have a big plant in California, just about 2 hours from here, which generates almost 10% of the energy in the state. It's about 2,000 megawatts of power, so this is just an enormous kind of base load, always operating source of energy. And there's a lot of concern a couple of years ago about this shutting down, but it was extended, at least for a few more years, to try to keep it running so that we would be able to meet the climate goals in California. Now, that's a microcosm of the problem, though, because if you look at the function of time, in the last decade or so, we have put very few reactors online. Basically, the energy from these large reactors has plateaued. There might be 1 or 2 that come online or have come online in the last decade, but it's essentially not happening. And one reason is just the cost. The way we build reactors in the US, for lots of complicated reasons, is extremely expensive. So we're not building them. So there's a lot of talk right now about building what's called a small modular reactor. They use slightly different technology, same basic physics, and make things that are less than 300 megawatts. So this was 2,000 megawatts, 1,000 per reactor. So it would be roughly a third of the size or less of one of those large reactors. And this is happening in the private sector. So there's companies, not many, but there are a few companies like NuScale and TerraPower that are actually building these. This picture, if you don't know who that is, if you zoom in, it happens to be Bill Gates, put a lot of money into this. And so there's effort going into building smaller reactors and doing it fast. Again, AI. Of course, if you have a reactor, if you read the news, again, it does make waste, right? So it makes waste products like uranium, strontium, and plutonium. These 2 are not necessarily a huge problem, but this one is. The half-life is 24,000 years, which means if you wait 24,000 years, you have half of it still there, being radioactive and dangerous. But, you know, we have solved other complicated problems in the history of humanity, and we could solve this one, I think. So in Europe and Finland, there are examples of success where people have dealt with the waste by putting it in a central location. The US hypothetically has something that will do this, but it is difficult to move the waste there and have it permanently stored, which is, I think, a big concern. But it is a solvable problem. So I'm almost out, or I'm out of time here, so I'm just going to spend a minute talking about fusion. So fission, you split these big nuclei, radioactive waste. Fusion is what happens in the sun. And basically, the process is that lighter nuclei are fused and release tremendous amounts of energy in the process. You can make heavier elements too in stars, like carbon and nitrogen, and eventually in supernova you can make things like gold. So this process releases lots of energy, happens in stars. Can we build a star on the Earth? People have been trying to do it for decades. It's always not that far around the corner. Right? That's one of the big problems with fusion. When I was in college, I don't think anyone told me you should be a plasma physicist and study fusion. But I do think that there have been some significant improvements that have made this more feasible. And so just to give one example, the previous ways that people would do this is either by making a big magnetic field and compressing a sort of gas called a plasma into something that would fuse. And the other approach is what we do in the US, which is using lasers Both of these approaches are massive experiments and have made progress, but aren't making power plants in the near future. What is interesting is the private sector. So this company, Commonwealth Fusion, I have no connection to them, but they seem to be very promising. They have raised billions of dollars in funding, and they seem to be on the path to actually making a fusion reactor. And one of the developments is that they've taken something from another field of physics, which is high temperature superconductors, to make magnets that can make this process work. And you'll notice magnets, that actually is related to what happens at a particle collider. So this is an article from CERN about how the magnets in future particle physics experiments overlap with fusion reactors. So again, science connects to other fields. Development in one area, fundamental science impacts other areas. So I want to kind of end this with a very speculative vision or proposal. Like, we have all these problems. What could we do if we thought more kind of conscientiously about the long term? And so this is just my own idea, just sort of back of the envelope about money. So where we are now, the yearly budget for the fusion reactors in the United States is roughly a few $100 million a year. It's like $700 million a year. You can't build something serious for that amount. I mean, it's amazing that they have done what they have, but the high energy physics budget is bigger than this, and we don't have the Large Hadron Collider in the United States. So you really can't do very much with this much money. Advanced reactors, that's even smaller, 100 million, right? The private sector is dumping money into both fission and fusion. So just to put a benchmark, when I wrote this talk the first time, in 2022, the estimate was about 2.5 billion in private funding for fusion. A little bit from the Department of Energy, but it doesn't seem to be very much. Now it's 10 billion cumulative into fusion. So people are just pouring money into this. $10 billion is about the cost to build the Large Hadron Collider. So private sector is pumping money into this. Will it be fast enough? Maybe. Certainly motivation in terms of the payoff. But another question is like, should we do this as a society? Should we invest in these problems? And so here's what I would propose. Increase the amount of funding for advanced reactor development, also for fusion, and then increase it again in 10 years. And that way, you could have renewables now, advanced reactors in the next 10 years, maybe even earlier actually, and then you could have fusion in about 20 years at a scale that would actually make a big impact on the globe. And I think in terms of the way other scientific projects have worked, this amount of money would make a substantial difference and probably make it successful. I haven't done a line item calculation of what it would cost, I don't know, but just looking at what we currently spend and kind of 10xing it, I think it would make a lot of sense. Okay, how does AI fit into this? No idea, but energy costs are going way up, or energy demand is going way up from data centers globally. So 10 years ago, it was less than 2%, now it's over 4%. So that is a really steep increase in energy demand. You've all read about this, it's in the news all the time, but you can't avoid this, right? But it is there, it's a big concern. The hope is that people would invest in things that will pay off, things like nuclear fusion and advanced reactors. This happened roughly 2 weeks ago in Congress. The CEO of Commonwealth Fusion testified about how they needed more money to roll out fusion reactors in the United States. Google invested in essentially an agreement to buy the first power from Commonwealth Fusion. So is this enough to offset the amount that is being used? Not at all. But it's certainly directionally right. So I want to end with this chart. If you haven't done this, Google En-ROADS calculator. I talked to you about renewable energy, fossil fuels, kind of how they work, and then why we use them, but strongly suggesting we should shift to renewables and nuclear energy. And the reason why is that if you look at the warming effect on the Earth as you kind of move these very simplified dials back and forth, in order to get to something that's under 2 degrees Celsius, which is the sort of target that we want to get to, you would really have to do everything on here. You have to stop burning coal, oil, natural gas, start renewables, max it out on nuclear, also fix things like efficiency and have electric vehicles, electrification of buildings, and a whole slew of other things that have more to do with like how we do agriculture, how we do sort of forest management, and potentially even carbon removal. So if you want to see, how serious is this to keep things under a given level, this tool will show you, yeah, it's very simplified, but I find it very helpful. So that's what I have. I'm happy to discuss things further in Q&A. And I did put a lot of links in this talk. If you want to take a few key ones or books, this could be a useful set of resources. And then I'm also happy to share individual articles if something, you're like, oh, I wanted to know what that small link was. I can share that as well. Thanks.
Can you talk at all about carbon capture and why we're trying to do it in the air as opposed to in the water?
Oh, good point. Air versus water. Yeah, so let's start with the first question.
Could you summarize the question for
Yes.
those who are watching? Thanks.
Absolutely. Whoops. I have something about carbon capture. Oh, I put it at the top so I wouldn't have to go all the way down. Yeah, so the question, very good question. Can you remove some carbon dioxide from the air? And do you need to do it? I think the short answer is that because we've already emitted so much, it probably is going to be needed. The issue is the cost. So what I can say is the cost at the source is much cheaper. So if you put it at the plant, it's much cheaper. This is actually not very expensive, $10 to $50 a ton. That's like adding $50 to your ticket to London, right? That's doable. Direct air capture is like if you put the plant on, ice in Iceland or something, where you have geothermal resources to power it. At the moment, this is very expensive. So this would be like, your flight costs $1,000, you double it. Not quite double, you add 500, so 50% increase in cost. So that's a lot. What I think is interesting is this chart here, where basically if you take what happened with solar, the cost really came down as you installed more of it. And so the argument is maybe you could take that kind of learning and apply it to carbon dioxide. Now, in terms of doing it on the water, I'm not totally sure what you mean.
My understanding is, which isn't much, it's a similar sort of technology. It's just that you get the benefit of the density of water and the chemical exchange.
I see. Yeah. So it's probably another way of implementing this. Yeah. I don't know about the cost of that, but I think really this is all about cost, energy to run it, and then the cost.
And go ahead.
Yeah.
You had the chart of the climate increasing temperature-wise of atmosphere. Is there something that correlates with what happens in the ocean with its heat sink and the carbon dioxide that's absorbed into the water?
Yes, both. Yes, I don't have a plot showing that, but they're both there. Yes. And
there's
the
a correlation between atmospheric warming and
Yes.
ocean warming.
For sure, there is. Yeah, I don't have an actual plot of that. That's an interesting plot, for sure. I mean, the one thing that I did show that shows that sort of indirectly is this plot. And this thermal expansion, it doesn't look like much, but this is like, that the water is basically expanding. So in my class, the students do this hypothetical calculation. The ocean is 2 miles deep. It warms up by 2 degrees. You know the thermal expansion coefficient of water. How much is it going to expand? And it's 6 feet, right? The problem with that calculation is that it doesn't warm uniformly. So you have to ask how deep you're asking about the temperature as well.
Any thoughts on geoengineering and whether or not we're going to have to rely on that?
Yeah, that's a good question. So geoengineering, the idea is that you would purposefully change the climate by emitting sulfur dioxide or maybe cloud brightening. and you would reflect some sunlight. So the idea is like, really basic physics, right? You have something that reflects some sunlight, and there's this concept, which I'll show you how we talk about this in physics. It's called the albedo. It's basically the reflection constant of the Earth. And so, like different things have different reflection constants. So the idea is like, well, we're obviously not going to like deploy mirrors in the surface, but you could inject just a little bit of something into the atmosphere. And so sulfur dioxide is one of them. And I talked about this with ships, right? We know that this happens. So it was like an unintentional experiment where essentially people showed that you could engineer the climate in this way. I don't know if it's necessary. I sort of think that another question is like how you would deal with this in an international level, because it's not just one country deciding to do this. It's going to impact the whole globe, and then there's going to be all these questions of like attribution. When there's a hurricane, like did you cause this because you geoengineered or not? So it just seems like very complicated politically, even if maybe it would be helpful to avoid the worst consequences, right? So I don't know how that would be negotiated, but it could have some useful effects. And the interesting thing is like also we have these experiments with volcanoes, and like you can stop putting sulfur dioxide in the atmosphere and then it kind of decays right away, unlike carbon dioxide. So yeah.
What is the half-life of carbon?
Carbon dioxide, I think it's like 100 years. It's very long. Sulfur dioxide is like less than 10 years. So it's very fast. So you basically just stop. The other thing is it's very cheap. So you can do it, the numbers I've heard are in the like tens of billions of dollars. So like it's at the point where an individual could do it.
Great.
Yeah.
DIY.
Yeah.
And I was just curious, on one of the maps, from like 1930 to about 1970, both the level of carbon dioxide in the atmosphere and global temperatures really flattened out. In fact, were somewhat coming down. I'm wondering, how does that, because you said if we stopped putting any CO2 in the atmosphere, it would still stay flat, for like 100 years. But I'm wondering if that's really true, or whether you really would start getting absorption, all the plants.
Oh, that's a good point. The curve, so
it was, one of the early slides.
yeah, so the bottom line question you asked, you can see it here actually. So actually it's not the clearest there, but basically there's a certain amount of warming that's baked in from the carbon dioxide, so that would take some time to remove. But you're right, eventually it would decay, but the time scale is in the like
Right,
hundreds of years.
but I'm saying in historical
Yeah,
facts,
I'm-
it
It flattened.
flatten.
I'm trying to
Even though
find
we continued to dump CO2. Yeah, that was it.
this one. Sorry, this one.
Yeah.
This is
Well,
sea level
that was
rise.
That was kind of when that's more temperature. Oh, sea
This is sea level rise. So this is because we built dams.
Right.
But there might be another effect with carbon dioxide levels.
Yeah, you had a plot where you plotted CO2 versus temperature.
CO2 versus temperature. This is the one. Yeah. It's,
And
here you mean.
yeah, it's sort of in the green going to
I see.
red, where there's actually essentially a drop in global temperatures.
Like right here.
Yeah.
Yeah.
And I mean, this was
Interesting.
a 40-year period. I felt like maybe there was another graph where it was showing the CO2 in the atmosphere versus time. And there again, it shows that same time period where it was sort of flat.
Yeah. I'm trying to think if I have a plot that shows enough resolution to see that 40-year period
Right.
closely.
What was the date range for that 40-year period?
1930 to 1970. 1934 was a real peak in global temperatures, and it went down. And that's why in the 70s, they actually talked about global cooling being a problem.
Are you talking about this plot?
Yeah.
You're talking about the temperatures. Yeah.
Well, yeah, temperature, I thought there was one where you had the CO2 versus the decades as well.
I don't think I showed that. I think I have it somewhere. But
Right.
So why does this happen to be flat?
Yeah, right.
Yeah.
Right.
Yeah.
And in fact, it's a net downward trend. You know, I mean, there's
Right.
lots of noise.
Yeah, so one of the reasons is, I think, that there just was less emissions that had cumulatively happened at this point.
Yeah.
So it's also a logarithmic function. So if you just kind of take any given snapshot down here, it's just not quite high enough to see the effect. And also, like the scale, I don't think that's what you're seeing. I agree with you, this looks pretty flat, as does this. But remember that we averaged in this region here. So we're saying like, this is our baseline. We haven't really done that much yet to the atmosphere. There's been relatively minimal emissions so far.
It might also be using different sources of coal that have more sulfur in them.
Oh, that could be, yeah, good point. Yeah.
I know that Westmont's done some things to try to reduce its footprint. Are you involved in any of that?
Yes, I am. What can I tell you that we have done? Well, so far we're trying to do a lot of sort of like book or research about what we actually have, and so one of the things that we sort of discovered is we have these buildings that are LEED certified buildings, and we probably should make a bigger deal about that. They're essentially efficient buildings, but looking forward, we're interested in trying to like calculate out what our impact is, and then think about ways that we could address some of those things. But a lot of them also come with costs, so yeah, but not a totally trivial problem. Yeah.
If CO2 keeps increasing, what is the tipping point, and what's going to happen?
Right. So the issue is tipping points, right? So tipping point refers to like when because the temperature is increasing, you unleash some other source of warming. And so I don't know exactly where the tipping points are, and I'm not sure that everyone knows where they all are. But the concerns are like you would release a lot of CO2 from like a yeah, from the tundra, for example. But I don't know where those numbers are. Yeah. I don't know if anyone else knows where they are, but I'm not sure anyone knows exactly the numbers for the tipping points.
And in some ways, it's not totally understood as well. I mean, there was 2 degrees centigrade above pre-industrial revolution was the target for a long time. Now there's talk about 1.5 degrees, which we're almost at. But everything it's a bit speculative because, I mean, you can have positive or negative feedbacks. In other words, if the temperatures rise, do other things happen that accelerate it? Or is there negative feedback? You evaporate more water, there are more clouds, it reflects more light, could be negative feedback. So there's a lot that isn't well understood.
Are there models that project?
So the models, I think, for the non-tipping point stuff are yes, like I made one, right? It's not very hard. The tipping points are the complicated ones because you don't know exactly what will happen. But like there certainly are models based on like the ancient history of the Earth. I don't know a ton about them.
Thank you.
Yeah, thanks for coming.